Magnetic forces on current carrying wires. Let's consider the force on a straight wire in a uniform magnetic field B. For a point charge, the force is F is equal to QV cross B. How about for a wire carrying a current? We should be able to use this same expression because the force will just be due to the motion of the mobile charges within the wire. So if we have a wire carrying a current toward us, as shown in this figure, and the magnetic field is to the right, as we expect from north to south, then if we use the right-hand rule, we know that the force will be upward. That's assuming a positive charge moving toward us. A positive charge would move in the direction of the conventional current in the wire. If this were in fact a negative charge, then the negative charge would be moving in the opposite direction of the current, and we would have V cross B is down, but QV cross B would still be up. So once again, the force would be up for a negative charge moving away from us or a positive charge moving toward us. We must have one or the other if the current is coming toward us. How big would the force be? Well, remember that I is equal to the concentration of charge carriers times the charge of each charge carrier times their drift velocity times the cross-sectional area of the wire. So let's consider the force on a section of length L of this wire. Now let's suppose there are total charges of capital N. That's the total number of charges in this section of wire of length L. The force on this length L would be F is equal to N, the number of charges, times QV cross B, where we'd use the drift velocity, of course. Now the number of charge carriers, capital N, is just be the number of charge carriers per unit volume, little n, times the volume, which is just A times L. So substituting back for capital N, we get NAL Q V sub D cross B. Rearranging, then we get NQ, drift velocity, times area, times L cross B. Well, the quantity in parentheses is just our current as we noted above. So this force is just I times L cross B. Here I've made L a vector, and I've defined the direction of L to be in the direction of the current in their wire segment. That's a nice little expression for the force, quite analogous to QV cross B for a moving charge. For a current carrying wire, we have IL cross B. That's handy. This in fact presents one way of measuring a magnetic field. Suppose we had a little section of length L in a uniform magnetic field as shown in this figure. The force is IL cross B. Well, in this case, L is to the right, B is out of the screen, IL cross B is down, and in fact it's perpendicular, so sine theta is sine of 90, so the magnitude of IL cross B is just ILB. So the force on that little segment at the bottom is ILB, so B is just F over IL. That's a nice little way of measuring the magnetic field. Measure that force for a given current. If we know the length in the current, we in fact know the magnetic field. And I will note that the force on the left and right segments of wire cancel, so we don't have to worry about that. Now let's look at a loop of current. A current coming up and going around this loop in a clockwise direction. Let's find the torque on this. We'll set this loop of current up so that it's free to swivel about a vertical axis. Well, let's look at the left section of wire carrying a current upward. The current is up, and so L, the vector L would be up. B is to the right, and so if we cross IL upward into B rightward, we get a force away from us. So the force on the left section of wire carrying an upward current is away from us. Similarly on the right side, the current is down, IL is down, B is to the right. Applying the right-hand rule gives us a force toward us. These two forces are tending to rotate the loop. Now, if the loop is mounted as above, we don't have to worry about any torques from the top or bottom sections of the wire. So these two side sections are the ones that are exerting the torque. Let's find the magnitude of that. For each section, recall F is IL cross B. They are perpendicular. The L and B are perpendicular for those two wire segments. And so then the magnitude of the force is just ILB. Now, the torque. Remember, the expression for torque is R cross F, where R is the distance between the axis of rotation and the place where the force is applied. And so the R in this case will just be W over 2, half the width. And so the torque will be a sum of two torques, the one from the left force, the one from the right force. So we have tau is equal to R cross F on the left wire plus R cross F on the right wire. Each of those will give us a torque of RF sine theta, where theta is the angle where the normal to the plane of the loop makes with the magnetic field. So from each of these we get an RF sine theta, total torque of 2RF sine theta. 2R is just the width. The width times the length is the area of the loop, and that gives us a total torque of IAB sine theta. The current times the cross-sectional area of the loop times the magnetic field times the sine of the angle the loop normal makes with the magnetic field. Let's take an overhead view of this same current loop. That is, we're going to be looking right down from above at this axis of rotation. Got that image? Let's go to the next screen. So looking down from above, we're looking right down the axis shown in the center. What was our left wire is shown right here, and the current is coming toward us. Remember, we're overhead, so what was an upward current is now a current coming toward us. The force, which was away from us before, is now toward the top of the drawing on that wire. Similarly, for the other wire, the current's going away from us, denoted by the crosshatch, and the force is downward. It's easy to see then that torque is clockwise. And you can see a little more clearly here the angle theta that we referred to in the previous drawing. Now, if we apply that torque, and if the loop is free to rotate under that torque, it will rotate another 45 degrees, taking us to this orientation here. The force on the left wire is still up, the force on the right wire is still down. We still have a clockwise torque. Let's let it rotate another 90 degrees. That takes us to this orientation. So looking at this, we now have no net torque because the top wire is experiencing upward force, the bottom wire is a downward force. These two forces are tending to stretch the loop, but they are not trying to twist it. So at theta equals 0, of course, sine of 0 is 0. It's no surprise that, in fact, we have no net torque. Now, were this current loop spinning, its momentum, its angular momentum, in fact, would carry it a little further to this orientation right here. Now, at this point, the magnetic forces on the wires are trying to rotate us in the opposite direction. We have a counterclockwise torque. And so, in fact, if we were to just set this up and let it go, it would spin and then rock back and forth about that vertical orientation. But what if, at the very moment we swiveled past vertical, we were to reverse the direction of the current? Then instead of having a counterclockwise torque in this last situation, we would have our currents reversed, our forces would be reversed, and in fact we would be right back to our original situation. And we would continue to have a clockwise torque, and we'd go another half turn. If we reverse the current again, we would go another half turn. We would continue to have a clockwise torque, spinning the loop under the power, in fact, of that current that we're driving through the loop. This is, in fact, a motor. We just made a motor by reversing the direction of the current at just the right moment when the loop passes vertical, as seen from above. Let's go back to our original diagram, but add in a way of doing that current switching. Boom, here we go. Look at this figure on the left. That's our current loop again, our north pole on the left, our south pole on the right. We have our two forces causing a torque on that. And down at the bottom, we have an interesting arrangement. The current is being fed from a battery. We have a couple of stationary brushes, but the wires are being fed by some contacts that slide between those two brushes. And you see the gap? At the very moment the loop is normal to the magnetic field, the brushes are over the gap, and in fact we're about to reverse the direction of our current. So this arrangement will reverse the current direction every time the loop makes a half rotation, just as we needed to make a motor. Those little split contacts are called commutators because they in fact commute the connection of the wires every half rotation. There you have a way of making a motor to run off a DC current. If we were to not use commutators, but in fact just hook a current up, but in fact build a spring to resist the torque of the magnetic field on the loop, we would in fact have an arrangement where the amount of rotation in equilibrium is proportional to the torque we apply. Of course, the restoring torque, that's a torsional spring, will be proportional to the amount of twist that the loop experiences. And so, in fact, in this case, the more current we apply, the more torque we get from the magnetic field, and the further we will have to rotate before we reach equilibrium with that torsional spring as shown in this figure. So there's another device that we can make from the forces of magnetic fields on current carrying wires. This is called a current meter. There's a practical one shown right there. If we feed the current one direction through the loop, the needle will deflect to the right. If we reverse the direction of the current, the needle will deflect to the left. The more current, the farther the needle will deflect. One more example here. This one's a little more complex. It is in fact an audio speaker. In this case, we have a magnet on the left. You can just think of it as a simple bar magnet, though it's a little more complex than that for an efficient speaker. And then we have a loop of wire through which we will feed a current. That coil is glued onto the cone so that when we get a current, it will experience a force in the magnetic field that moves the cone forward or back. As we reverse the current, it will in fact shake the cone back and forth. If we feed an alternating current that is proportional to the pressure of the sound waves coming from an audio signal, we will in fact cause a shaking of the cone that reproduces that sound. Now, why this causes a net force, I'll leave that to you to figure out. We did it for a current loop. This is also a current loop, but a little different situation. We're not looking at a torque here. We're looking at a force to the left or the right, depending on whether the current is going around one orientation, or going around the loop in one way or the opposite direction. So I'll leave it to you to draw the force diagrams to find the direction of the net force. But one hint, do not assume the magnetic field is uniform. Draw the magnetic field as it would be off the end of a magnet. The diverging magnetic field lines are key to be able to understand how the net force on this coil arises. So think about that and see if you can figure out why we get a left or right force on the coil and therefore on the speaker cone. Before we close, I want to offer special thanks to the authors of College Physics at OpenStax College. who were the sources of many of the figures we saw. Also wanted to thank Wikipedia and Wikimedia Commons, the contributors to those sites that also produce some of the figures we've seen in this video. Thank you very much for watching.